Right now, a 100,000-ton monster is rising from the depths after 15 months of emergency surgery. The USS Gerald R. Ford, the Navy's $13 billion pride, almost became a catastrophic failure when its guts tore apart mid-ocean. Engineers found something during repairs that terrified Pentagon officials. The fix they performed just rewrote naval engineering forever. They're hiding the real reason this happened from the public. Smash that subscribe button immediately, because what you're about to witness will blow your mind. The billion-dollar breakdown. The USS Gerald R. Ford's propulsion system generates enough power to light up 100,000 homes, yet a component smaller than a car engine brought this technological titan to its knees. In March 2018, during what should have been routine testing off the Virginia coast, vibration sensors detected something impossible. The main thrust bearing, a precision-machined component weighing 8,000 pounds, was disintegrating at 200 revolutions per minute. The bearing's internal temperature spiked to 487 degrees Fahrenheit, well beyond its 350-degree operational limit. What made this terrifying wasn't just the failure itself, but the timing. The Ford was operating at only 60% power when catastrophe struck. Naval engineers ran the calculations and discovered a nightmare scenario. If the bearing had failed during full combat operations at maximum thrust, the resulting shaft seizure would have generated enough friction heat to potentially breach the hull integrity near the reactor compartment. The repair cost alone hit $284 million, but that number doesn't include the operational losses. Every day the Ford sat in dry dock, the Navy lost $2.1 million in potential deployment value. Over 450 days of repairs translated to nearly $950 million in lost operational capability. But here's what they're not telling you about those repairs. The bearing wasn't the only component that failed. 3 other critical systems showed stress fractures that shouldn't have existed on a ship this new. Nuclear power's hidden weakness. The Ford's 2A1B. Nuclear reactors produce 700 megawatts of power, 3 times more than any previous carrier. This massive energy output flows through a propulsion system that weighs 2,700 tons and spans the length of a football field inside the ship's hull. The main reduction gears, each the size of a school bus, convert the reactor's steam turbine rotation from 3,600 RPM down to just 150 RPM for the propeller shafts. Between these massive gears and the 4 bronze propellers sits the thrust-bearing assembly. These bearings don't just support weight, they absorb 280,000 pounds of forward thrust force, generated by those 66,000-pound propellers churning through the ocean. The bearing that failed was manufactured by General Electric's Marine Division using a process called Babbitt metal coating. This soft metal alloy, invented in 1839, gets poured at 800 degrees and must cool with absolute precision. A temperature variance of just 15 degrees during the cooling process creates microscopic crystalline structures that will fail under sustained load. Metallurgical analysis revealed that GE's quality control missed a 23-degree temperature spike during the coating process. That single manufacturing defect created a molecular weakness that took 18 months of operational stress to manifest. The Navy quietly tested all 8 remaining thrust bearings across the ship. 2 more showed early-stage crystalline fracturing. They hadn't failed yet, but they would have within 6 months of continued operation. What's even more disturbing is what they found in the backup systems. If you're as shocked as we are about what's happening with America's most advanced warship, do us a huge favor and hit that like button right now. Subscribe and turn on notifications, because the next part reveals technology that's keeping our enemies awake at night. The Dry Dock Operation. Huntington Ingalls Industries operates Dry Dock 12 in Newport News, Virginia, the only facility in the Western Hemisphere capable of handling a Ford-class carrier. This engineering marvel measures 2,400 feet long, 256 feet wide, and 46 feet deep. The dock's pumping system can move 18 million gallons per hour, yet emptying it completely still takes 11 hours of continuous operation. Positioning the Ford required 6 ocean-going tugboats, each generating 6,000 horsepower, working in perfect coordination. The alignment tolerance was 4 inches over the carrier's 1,106-foot length. Missed that mark by even 6 inches, and the ship's keel blocks could punch through the hull plating when the water drains. GPS tracking systems monitored the ship's position to within 0.8 inches in real time. Once positioned, workers placed 662 wooden keel blocks beneath the hull, each precisely machined to support specific load points. These blocks, made from Douglas fir, can support 40 tons per square foot without crushing. The total weight distribution calculation took 3 structural engineers 14 days to finalize. When the dock finally drained, 326 workers descended on the exposed hull within 90 minutes. Time was critical because every 24 hours in dry dock cost $3.7 million in facility fees alone. The thrust bearing replacement required cutting through 8 inches of hardened steel deck plating just to access the shaft assembly. Removing the damaged bearing took 72 continuous hours using hydraulic jacks that exerted 450 tons of force. But the bearing replacement was just the beginning of what they discovered once inside. Technology that terrifies enemies. While repair crews worked on propulsion, weapons specialists conducted tests on the electromagnetic aircraft launch system that revealed something extraordinary. Traditional steam catapults slam aircraft from 0 to 165 miles per hour in 2.5 seconds, subjecting pilots to 3.5 G-forces and airframes to structural loads that reduce aircraft service life by 15%. The Ford's EMALS applies force gradually across the entire launch stroke, reducing G-forces to 2.1 while increasing end speed to 175 miles per hour. This seemingly small improvement translates to launching 4,320 additional aircraft over the carrier's 50-year lifespan before reaching the same accumulated airframe stress. The system's 284 megajoules of stored energy can launch a 100,000-pound aircraft every 45 seconds indefinitely. During testing in dry dock, engineers pushed EMALS through 847 consecutive launches without a single failure. The previous record was 400 launches before mandatory maintenance. But EMALS represents just one piece of the Ford's technological advantage. The AN-S3 and AN-Y. 4 dual-band radar system simultaneously tracks 876 targets while guiding 24 missiles and coordinating air traffic for 75 aircraft. The system processes 4.7 terabytes of data per hour, equivalent to streaming 940 Netflix movies simultaneously. Chinese naval intelligence attempted to acquire this radar technology through cyber espionage 17 times between 2019 and 2023. Every attempt failed because the software operates on custom-built processors that physically cannot run code from external sources. What they found during the radar system testing, though, changed everything about carrier defense. The 6-month secret. Between April and October 2023, while the Ford remained in dry dock, Navy technicians conducted classified tests on the advanced arresting gear system that stop landing aircraft. Standard arresting cables must be replaced after 125 aircraft recoveries because the repeated stress causes internal wire strand failures. The Ford's AAG uses a water turbine braking system controlled by software that adjusts braking force 3,200 times per second during each arrested landing. This precision reduces cable wear by 340%, extending replacement intervals to 428 recoveries. During testing, they discovered the system could safely recover aircraft weighing up to 57,000 pounds, 7,000 pounds heavier than design specifications. That margin means the Ford can recover aircraft that would have to ditch in the ocean if approaching a Nimitz-class carrier with battle damage and full weapons load. The testing also revealed something unexpected. The AAG's precision control allows recovery of damaged aircraft with asymmetric drag characteristics that would cartwheel across the deck of conventional carriers. Engineers simulated recovering an FA-18 with one engine out and half a wing missing. The AAG made 847 micro-adjustments during the 1.8-second arrestment, and brought the aircraft to a perfect stop within 2 feet of the optimal position. This capability alone could save billions in aircraft that would otherwise be lost. The USS Gerald R. Ford just proved that American naval engineering doesn't just survive failure, it comes back stronger and more dangerous than ever. This $13 billion supercarrier spent 15 months getting rebuilt from the inside out, and what emerged is a vessel that redefined modern warfare. If this breakdown of military technology opened your eyes to what's really happening on our oceans, hit that like button and subscribe right now. Drop a comment telling us which part shocked you the most, and we'll see you in the next one.